Hello Bobcats. Today we'll be discussing limiting reactants. Now a limiting reactant is the substance that limits the amount of product that can be made. The limiting reactant is the substance in a reaction that limits the amount of product that can be made. That can be produced. Let's say produced instead of made. So that can be produced. So you can't make any more than what is allowed by the limiting substance. In fact, the limiting reactant is the substance that gets completely consumed in the reaction. So it is the substance that is completely consumed in the reaction. In the reaction. So that you should have none of this left when the reaction is complete. And then the other would be the excess reactant, and the excess reactant is not completely consumed in the reaction. The excess reactant is the substance that is not completely consumed. It's what is left over, if you want to say it that way. So it's not completely consumed in reaction. And we can say that it is the leftover reactant. So it's what's left over or remains. Leftover reactant. Okay, so when you have a limiting substance problem, you have to determine what the limiting substance is. In other words, what is going to limit how much you get to make. And there are certain things that we need to do for limiting reactants. Let me get this straightened out here. Sorry about that. And so let's go through the process or what it is required to solve a limiting reactant problem. So solving a limiting reactant problem. Now, the first thing we have to do when we have a limiting reactant problem is recognize that it's a limiting reactant problem. And how do I recognize that I'm actually working on a limiting reactant problem? So you know the problem is a limiting reactant problem. When there are amounts of 2 or more reactants. When there are amounts of 2 or more reactants. If you only have the amount of one of the reactants, you don't have to worry about doing the limiting reactant problem. Because you don't need to figure out what limits. There's only one amount, so that's what you work with. So you do a basic stoichiometry problem. But when you have 2 or more amounts, you have to figure out which one is limiting. And so to do that, first thing you need to do, number one, is write a balanced chemical equation, because all stoichiometry is based on the coefficients of a balanced chemical equation. And I should say balanced right here. Balanced chemical equation. So that's very important. So anytime you have a chemical equation, make sure it's balanced. Now, the next thing you need to do, number 2, is you have to identify the mole amounts of each reactant So identify the mole amounts of each reactant that you have. And it's important to know that you're identifying what you have. So what I mean here is, like, if you have the mass of a substance, then you want to change that to the mole and find the moles. If you have a volume of it, you got to figure out the moles of it. You've got to change whatever you have to the moles of what you have. Again, it's my saying, you have to go to the mole. So make sure you go to the mole for both of the reactants, and this is what you have. The next thing is, you need to determine the mole amount needed of one of the reactants, of one of the two reactants or three, of one of the reactants by using mole ratio of both reactants. What this does is it determines how much of one reactant is required to react with all of the other reactant that's available. Number 4, then you have to decide what reactant is the limiting one. Decide the limiting reactant by comparing what is needed to what you have of the reactant you chose. Well, let's not say of what you chose, because that might confuse you. What you have. Okay, so what is needed to what you have. Then the last thing is, once you know what your limiting reactant is, then you use limiting reactant. So you always start with the limiting reactant. So you use the limiting reactant amount to determine the amount of products formed and you also use the limiting reactant. So again, you're always starting back with the limiting reactant. It's very important that everything after you found the limiting reactant uses the limiting reactant. So you use limiting reactant amount to determine amount of the other reactant used which is the excess reactant. And I'll just put excess underneath here so you know that's what we're talking about. The excess reactant used and amount remaining. So now what we're going to do is we're going to take an example problem and we're going to go through each one of these 6 steps. And I'm going to carefully discuss them and identify them each step as we go along. So the next part of this is to do a practice problem to identify each of the steps. So what we're going to do now is we're going to look at a problem, and that problem will be the following. So let's do an example problem. Example problem. So limiting reactant example problem. So the first thing we need to do is determine the limiting reactant. When 18.1 grams of ammonia reacts with 90.4 grams of copper 2 oxide to produce nitrogen gas, solid copper, and water vapor. Okay. Then after we have determined the limiting reactant, the second thing we're going to do is determine the mass of of nitrogen gas and solid copper that is produced. So in this case, we're going to determine the amounts of each product, or 2 of the 3. We're just going to pick 2 of them. Then the next thing we need to do, number 3, is determine the amount of excess reactant in grams. So determine the mass of excess reactant that remains. Now, it's kind of redundant saying it this way, because really when they say excess, that means there is stuff that remains. So probably from now on I'm just going to say determine the mass of excess reactant, or determine the amount of excess reactant. So these are the 3 things that we need to do. So we're going to follow each step along the way. Now the first step, again, is to write the balanced chemical reaction. So the first step, number 1, is write the balanced chemical reaction. So we're taking ammonia reacting with copper 2 oxide. So ammonia plus copper 2 oxide produces nitrogen gas, which is N2, plus solid copper, Cu, plus water vapor, H2O. Now we have to balance it. And so in this case, when we balance, I look here and I've got 2 hydrogens and I have 3 hydrogens. Or I can even see I've got 1 nitrogen and I have 2 nitrogens. So that means I need to put a 2 here. So now I have 2 nitrogens and I have 6 hydrogens. I only have 2 hydrogens here. So I need to put a 3. When I did that, I made 3 oxygens. So I go back and look, I've got 1. So I need to put a 3 here. And then from that 3, I've got 3 coppers, 1 copper, I have 3 there. So my ratio is a 2 to 3, don't forget 1 to 3 to 3 ratio. Now I'm going to put my information below each one of the substances. So in this case, we are reacting 18.1 grams of the ammonia with 90.4 grams of the copper 2 oxide. Now, it's important here to understand that you cannot determine limiting reactant from the mass, because even though this is more mass than this one, this may be the limiting reactant for a couple of reasons. This is a different mass than this is as far as the compound goes, and then they react at a different ratio, a 2 to 3 ratio. So the first thing we need to do, so the next step in determining limiting reactants was to figure out the mole amounts of each substance. So here we have 18.1 grams of ammonia, and we got to convert that to the mole. So we know that 1 mole of ammonia, and this is the molar mass, 1 mole of ammonia has a mass of 17.04 grams for ammonia. So I'm going to convert grams to moles using molar mass. And so now this says that I have 1.06 mole of ammonia. And I'm going to write that I have this so I don't lose track. So I have that much. And definitely go 3 sig figs on everything, because we have 3 sig figs. So do minimum of 3. 4 might even be better, but a minimum of 3. Next, we're going to take the 90.4 grams of copper 2 oxide, and we're going to convert it to the mole using molar mass also. And the molar mass of copper 2 oxide is 79.55 grams of copper 2 oxide. So when I do that, I get moles 1.14 mole of CuO, copper 2 oxide. This is what I have. So these are the amounts. So the 18.1 grams is really saying that I have 1.06 moles of ammonia, and the 90.4 grams says I'm really saying that I have 1.14 moles of copper 2 oxide. Now I still cannot determine what's limiting based on these values here, because this doesn't account for the ratio that they react with each other. So do not stop here and say, oh, ammonia must be limiting because it's less. That does not work. You've got to do one more step. And so the next step, which is the third part of the problem, would be to take one of the amounts. It doesn't matter. I'm going to just start with the top one. So I'm going to say 1.06 moles of ammonia, and I want to find out how much of the copper 2 oxide will react with all of that 1.60 moles. And to determine that, I use the mole ratio. So we have 2 moles of ammonia will react with 3 moles of copper 2 oxide. So 2 moles of ammonia will react with 3 moles of copper 2 oxide. Now in this, when I do this, now I say that this will come out to be 1.59 moles of copper 2 oxide, because remember I canceled the ammonia, so I'm left with copper 2 oxide. That's what I need. So I need this much copper 2 oxide to react with all of the ammonia. That's what I'm saying. I need this much to react with all of the 1.06 moles of ammonia. Well, I have 1.14 moles. I need 1.59. I do not have enough. I only have 1.41, so I do not have as much as I need. So therefore, this is the limiting reactant. Now I put a square around it and identify it so I don't lose track. So there's my limiting, copper 2 oxide. Again, remember, this is how much I need, this is how much I have. I don't have enough, so it limits the reaction. So now the next part, part 4, now I know what's limiting. I'm going to figure out the masses of the amounts of each product. In this case, I want to know the moles of each product. I mean grams, sorry. It says determine the mass of nitrogen gas in solid copper. So I want to know how many grams of N2 and how many grams of copper. So let's start out. I'm going to again start with the limiting reactant. So I'm going to start with 1.14 moles of copper 2 oxide. That's my limiting. By the way, this is step 4 of those procedure that I told you about earlier. Now I have moles of this. I don't have to convert. Some students want to convert right away, do a molar mass. No. Please don't do that. We're already in the mole. And if you're in the mole, we're going to convert from copper 2 oxide to nitrogen. So we're going to compare these two, because that's what I'm looking for, is the nitrogen. So I'm going to say for every 3 moles of copper 2 oxide, so I'm going to do my mole ratio, I'm going to produce 1 mole of nitrogen gas. Now remember, I started with the limiting, doing my mole ratio to convert from copper 2 oxide to nitrogen gas, and then we want mass, so I got to go from moles to mass using molar mass. So 1 mole of nitrogen has a mass of 28.01 grams for nitrogen. Now when I do this, I get 10.6 grams of nitrogen. So this says that I should be able to produce 10.6 grams of nitrogen when I react 90.4 grams of copper 2 oxide, which is the limiting reactant. I need to get a different pen. This one's going out on me. And then next one, we need to find out the amount of copper produced. So again, I'm going to start with my limiting reactant amount, which I put a square around so I don't lose track. That's 1.14 moles of copper 2 oxide. I'm going to do a mole ratio of copper 2 oxide to copper in this case, because I'm going from this limiting reactant to the mass of this one. So it's a 3:3 ratio, which can be reduced to 1 mole of copper 2 oxide for every 1 mole of copper produced. Cancel. Now I want grams, I don't want mass, so 1 mole of copper has a mass of 63.55 grams. That's molar mass. And now that gives me the mass of the copper. And this comes out to be 72.4 grams of copper. So if you look in this part, what I've done is I have determined the amount of each of those products. So these are the products. So I'm taking my limiting reactant and determining, this is my limiting reactant, and determining how much of each of the products I get to make using my stoichiometry, which is this mole to mole ratio between substances. Now the last one that we have to do is we have to determine the mass of excess reactant that remains. So again, I start with, so that was the 5th one on the things to do. I'm going to start with the amount of limiting reactant. Remember, we always start with limiting reactant once we have the limiting reactant. Now, again, I'm now trying to find excess reactants. So I'm going to do the mole to mole ratio of my reactants. Think of the words that we're talking about. We're talking about reactants now. So I'm going to do a 3:2 ratio of copper 2 oxide to ammonia to determine how much ammonia was used. So 3 moles of copper 2 oxide, let me move this up, of 3 mole copper 2 oxide will react with 2 moles of ammonia. Now, I don't want the moles of ammonia. I need to figure out the mass so I can subtract it from this. So I got to go to grams. So molar mass, 1 mole of ammonia has a mass of 17.04 grams for ammonia. Okay, that's gone. And now I just multiply and divide, and I'll get 13.0 grams of ammonia is used. That's how much is used. Not how much is left over. That's how much is used to react with all of the copper 2 oxide. So I start with the original amount, 18.1 grams minus 13.0 grams, and I have 5.1 grams of ammonia remaining. So that's how much remains. Okay, again, I'm going to go back through the steps. There were 5 steps. We know that we have a limiting reactant problem because we have the amounts of 2 reactants. The first step in solving these problems is always get a balanced chemical reaction, because it's the coefficients that we're going to use to solve the problem. Then the next step is to find the mole amounts of each of these substances. Now we're in mass, so we have to go to mole, so we're going to use molar mass to convert to the mole. So we take the mass, molar mass, and that gives me 1.06 moles of this reactant and 1.14 moles of this reactant. This is what I have. Now I write have so I don't lose track. The third step says determine the mole amount needed of one of the reactants by using mole ratio of both reactants. So I'm going to just pick the top one. It doesn't matter which one you pick. They'll both work. You just have to interpret it correctly. I start with 1.06 moles of ammonia. Mole ratio, this tells me that for every 2 moles of this I have to react 3 moles of the copper 2 oxide, and that means I need 1.59 moles of copper 2 oxide to react with all of the ammonia. So if I need this, and I write need so I don't lose track, if I need this and this is what I have, I don't have enough. Therefore that is limiting. So I identify that. The next step is use the limiting reactant to determine products. So I start with the limiting reactant each time, and I do the mole ratio with the product that I want. In this case, 3 moles of copper 2 oxide to 1 mole of nitrogen gas. Use molar mass, and I find the mass of the nitrogen gas. Start again with the amount of the limiting, that's why I identify it, and then do the mole ratio of the copper 2 oxide to the other product, copper, and that's a 3:3 or 1:1 ratio. Molar mass, get the mass of that product. And then the last one is to determine the mass of reactant, excess reactant used, and then how much is remaining. So again, I start with the limiting reactant amount that I had identified. My mole ratio of reactants, 3 moles of copper 2 oxide will react with 2 moles of ammonia. Go to the mass, find the mass of ammonia used. Okay, that's the mass used. Then I take the original mass, subtract the mass used, and I get the mass remaining. And that's a limiting reactant problem. And I will talk to you again later. Bye.